Today's lab, Unit 2 is about capacitor and capacitance. A capacitor is a device that can store electric charge, and you can see in the figure we see top plate has negative charges and the bottom plate has positive charges. Also, the electric field is directed upward from positive charges towards the negative charge, and the plate separation is uh, distance d. The top plate and bottom plate have two different potentials denoted by VA and VB. A capacitor, this device, it consists of two conducting parallel plates, as you can see, and they are usually placed near to each other. This distance will vary how much charges the plates can hold. We'll see that in a minute. And so to start, let's derive a capacitor formula that we derive from the idea that how we can store or put charges in the plates uh, and what affects how much charge we can place there. Uh, so this is a simple example of parallel plate capacitor. Here are two plates that are connected to the potential source. This battery here provides the required potential difference uh, for charges to move around this conducting wire. So it's pushing the electrons towards the negative towards this plate here, which gains net minus q charge, and that results in the positive plus q charge in the opposite side. And this is our parallel plate capacitor. Now this is a device that's storing the charges that we got from the battery. Actually, battery help to put the charges in the plates. So how much charge we can store here uh, depends on the potential difference the battery can provide. So therefore, stored charge Q is proportional to the voltage V, and we replace that proportionality constant Q proportional to V, and that proportionality sign is replaced by a constant C called the capacitance of the capacitor. And now that capacitance tells us the physical ability of these two parallel plates to hold charges. And that capacitance of the capacitor is again is a function of the geometry of the capacitor. So that C capacitance depends on the area of the plate and the separation distance. So it's directly proportional to area, inversely proportional to the distance, and that proportionality sign is replaced by another constant called epsilon naught. This is the same epsilon naught you saw for electric force and electric field. That epsilon naught value is 8.85 times 10 power negative 12 coulomb square per Newton meter square. And so what this means is how much charge we can store in the plate increases by increasing the area. Larger the area, bigger the capacitance of the plate. And if we can decrease the distance between the plate, we can increase the capacitance. In other words, if you increase the distance between the two plates, you would decrease the capacitance of the plate. So again, capacitance of the plate is a geometrical property that depends on the area and d, and epsilon naught is constant. Again, what is epsilon naught? It's the We also call the electric constant, or it's the permittivity of free space. In the previous figure, you saw the electric field, going from positive charge to negative charge. As soon as the negative charges are deposited in the plate, electric field sets off between the plates. So that electric field traveling from positive to negative has a finite speed. So meaning the speed of those electric fields are dictated by the space itself. That's what it means. The permittivity of free space. The free space permits the electric field to travel at finite limit. It's not infinite. And later in this course, you'll see how light is made up of uh, uh, electric field and magnetic field. So the speed of light consists of the electric field constant epsilon naught, and from here you can derive the speed of light, which is finite. um, we'll see that when we do electromagnetic waves. But for now, again, these two equations should suffice to do our labs. Most of the laboratory works. Again, charge Q equals to CV. This is the most standard equation in capacitors. And C here, this is same C as here. The capacitance of the capacitor depends on the area and the distance. The unit of capacitance is farad, F-A-R-A-D, or symbol is just capital F. And 1 farad from here, you can say 1 coulomb per volt. Okay. And we can store energy in the capacitor, or by storing charges, we are automatically, giving the electric energy. Potential energy. We are storing electric potential in these two plates. And that energy, comes from the fact that we have to do some work to, bring charges and store in the plate. The voltage here does that work. The potential does the work to bring the electrons and, leave it in these plates. And now the plate has overall energy called the electric potential energy, meaning it has tendency to do work in the future. Even if I disconnect the wires now, so now the plates are charged, let me disconnect the wire, the charges are going to remain in the plates. And now if I had to remove the voltage source, the potential source, and connect a small light bulb here, then the charges would will move through the light bulb, and that potential energy now would be converted into the light and the heat energy. We'll see that in an experiment in a minute. We can put this is one capacitor. The symbol for a capacitor is two parallel lines. For a voltage source, it will be one longer and one shorter line. Longer line is always positive, shorter end is always negative, even you don't see plus or minus. But here these are two parallel lines. We can put these capacitors in multiple way. Um, Here first one would be the capacitors in series, one after other. I can put right next to each other, or bend the wire and put here or here. I can put as many capacitors as I want. This is a series combination, and in series combination the equivalent capacitance would be 1 over C equivalent. The inverse of equivalent capacitance is sum of inverse of each of the capacitors, or each of the capacitance values, and C equivalent from this relation is C1 C2 divided by sum of C1 and C2. And the other possible combination is when capacitors are placed in parallel to each other. So this would be parallel combination. Again, that's the voltage source here. And in this combination, the equivalent capacitance, the equivalent capacitance of the system, C1, C2, I can add C3, C4, however many capacitors I have. the equivalent would be the algebraic sum simple C1 plus C2. Any questions? And so these are all equations that you will need to complete today's lab. Now let's move on to our lab exercise. So here's the lab manual for this lab. As usual, complete the top portion with your name, IDs. Due date is tomorrow at midnight. Uh, and again, start with the theory. Complete the theory section, and um, and as I have asked in the past, try to complete your pre-labs before coming to the lab. Um, you'll have basic idea of the coverage for the day, and so each pre-lab is worth 1 point. Once you complete your pre-lab, start the lab by opening the simulation here. This is your Capacitance Lab Simulator, and you may need to do back and forth. So here, the first question is identify what features of a capacitor can be maximized or minimized to make a capacitor with the greatest capacitance or least capacitance. So I would like you to, play with this simulation, uh, explore it. Here are some connectors that you can connect the plate to the battery source or disconnect it. You can change the battery voltage from here and this arrow here. I'll usually work with the positive voltage, so 0 to plus 5 or the maximum voltage. It says it goes up to 1.5 volts. And here I may want to record see what they stored energy in the plates. In the theory section, if I miss the potential energy, uh, here you can see the energy stored in a capacitor is half CV square. You can write it as half capacitance times voltage square or half QV, charge times voltage. Either way, in theory section, you can use either of these formula depending on what variable is given to you. Here the stored energy will be calculated as we change the parameters. You can use this. So let me connect it to the battery. Now it's connected, and I can change the plate separation from this using this arrow here. That's the minimum distance I can go is 2 millimeter, as much as 10 millimeter. I can also change the area of the plate. The capacitance of the capacitor again depends on the um, the separation distance and the area. We're not using dielectrics. Here dielectric would be any material placed in between the capacitor. Right now we're considering air as the medium. uh, you cannot have any conductor touching these plates, then it would be a short circuit, and the charges would just flow and you would not have a capacitor. So these capacitor plate, you can bring them as close to each other as possible but not touching. So that means we would need an insulator in between the plate at all the times. And the other way to increase the capacitance would be to have a dielectric, meaning an even better insulator than the air itself. Why? Because if you put enough charges in here between the two plates, the electric field gets so strong that the air ionizes in between and electrical discharge can happen. So we would need very good insulator, even better than air, and that would increase the capacitance of these plates as well. But for now, we're not using any dielectric other than the air itself. So the separation distance is limited to 2 millimeter. You can you can increase that up to 10. You can also change the area, and now by changing, you can change the voltage. Your Q equals to CV. Your charge stored here is proportional to volts, so you increase the volts, the charge would increase, and also your potential energy you see, increases. And that would do the first part. In the second one, it's asked to design the experiment to find the relationship between the charge, voltage, stored energy for a capacitor. So in the same experiment, we are changing the voltage. Voltage values are given, and as we change the voltage, let's see how charge, capacitance, and energy of the capacitor changes, and uh, write down um, what you observed about the capacitance and the energy stored. So here the potential we can change from 0 to 1.5. So we'll start at 0. Of course, there is no uh, charge because Q equals to CV. V0, charge 0. Let's give some voltage here as it says 0.15 volts. How do I measure 0.15 volts? I have a voltmeter here. Let me bring that voltmeter and connect my probes. Again, the red is always positive. That's the convention. Let's just stick to that. Um, and so right now it's at 0, so 1.15. If I can work with my trackpad here. Okay, so as my voltage here is 0.15, there are a certain amount of charge here. Can I read the charge? Top plate charge. I can even read the charge, how much charge it placed in the two plates. That PC is picocoulomb. P is pico. So it's measured. The standard unit is farad, but since the 1 farad is requires a lot of charges, uh, and we're dealing with a 1.5 volt battery, so we can assume the capacitance of this thing here for that separation and that distance it's only 400 millimeter square. It's a very small capacitance value. Pico is 10 power minus 15. Okay, and coulomb 0.05 times 10 power minus 15 coulomb, or zero point zero 0.05 picocoulomb, and that's picojoules. So it's almost zero. So the realistically the energy stored is zero for when the volt is 0.15. However, I can increase that. So here in the graph, you say it asks you to get data for different values of voltage. And let me just jump to 1.5 volts. Then I get some measurable energy of 0.4 picojoules, 0.53 picocoulomb, and 0.35 um, picofarad. What I can do now, I can decrease the area. What happens, you see the capacitance should increase because capacitance is epsilon naught A over D. D is at the bottom. So if you decrease the distance, capacitance increases. And that's what we see it here, right? And by decreasing the area, however, everything decreases. If I increase the area, my capacitance increases. Hence the stored energy increases. Okay. And that's what we're doing on table 1 and 2. First, we are changing the voltage. Second, we are changing the distance. And third, we are changing the area. And we are observing how the charge, capacitance, and energy stored in the capacitor varies. Okay, and write what you have found. And also, if you wanted to design a capacitor system to store the greatest energy, what would you use? It's a good question. So here, as you can see, stored energy. From here, what we learn is to have the maximum stored energy of 1.99 picojoule Like if when I had the distance increased, I had a smaller energy. So that energy increases by decreasing the distance, and same thing with the uh, area, right? The other thing I can do is now, so once I charge the capacitor with 1.5 volts, it attains some charge. So that's, let me do that at minimum distance and maximum area. I would have the maximum charge, 2.66 picocoulomb. Now what happens is when I disconnect it from the battery source, let me disconnect that. So you see, nothing changed in terms of charge, and that's right. We simply, so there were charges stored in the plates, and by disconnecting it in the battery, the charge remains constant. The charges remain within the plate, right? And so these are my values: capacitance, top plate charge, and the stored energy is 1.99 joules. So now I have charges stored in the plate, and that's the function of the capacitor. Now let's explore what happens when you increase the separation or decrease the area. So now what's the top values for the stored energy and capacitance? What should happen when I increase the separation? The capacitance should decrease because it's inversely proportional to the distance. And so as you see, the capacitance decreased by increasing the distance. But now what happened with the stored energy. Stored energy was 1.99 picojoules. Now it went up by 5 times, so almost 10 picojoules. So by once you disconnect it from the battery, and now if you increase the separation, your potential energy also increases. And what happens by changing the area? So from 9 joules, your energy goes to 39 picojoules. However, the capacitance should decrease because capacitance is directly proportional to area, inversely proportional to distance. You decrease the area, your capacitance decreases. You increase the area, capacitance increases, but it's inversely related to the energy. If there are three energy relations, this is also important concept for your class, for your theory class, okay, for exams. Uh, if you look at the formula, your potential energy, I can write it as half Q square over C. Okay, Q here is constant. We are not changing charges that are in the plates. Okay, so your energy is dependent on capacitance only. So potential energy is Q squared divided by C, and your energy is inversely related to the capacitance, and capacitance has relation to the distance and area. So by decreasing the separation distance here, decreasing separation distance meaning I'm increasing the capacitance, and for the energy formula, that energy is half Q squared over C. So as C goes down, so in this case here, as C goes down, your uh, potential energy goes up. And here, and that C has built-in separation and area in it. So changing area and the separation directly affects the stored energy. And how it affects, again, look at the formulas. Q equals to CV, capacitance C is epsilon naught A over D, and your energy is half Q squared over C. That should explain these three features that we just observed between separation area and the energy. And next, I Next is the light. So uh, I can, it's a slightly different setup. It's still a capacitor. Now I have a light bulb that I can hook up to the capacitor. Here, the goal is to see what happens to the charges when we connect it to the light bulb. So first, let's charge the capacitor. So let me give some voltage to it. Maybe um, provide some potential and charge it, and again disconnect it. The charges remains there. Now let me connect it to the light bulb. So when I connected it to the light bulb, the circuit is complete in this way. So meaning, all the negative charges charge here. So you see all the negative charges in the plates flow through the uh, light bulb and gets to the positive plate, neutralizing the positive atoms here. And as the electrons travel through the high resistance material inside the bulb, the electrons here loses energy, and that energy, so all this potential energy, lost potential energy, is converted into light and heat energy. So that's called the energy dissipation, and that's how the light bulb gets lit up. And so you see, currently it has finite amount of charge. So when all the charges are used up, the light goes off. So first it glows very bright because there are many charges stored here, and as charges, as the energy dissipates or the charges decreases, then the light bulb goes off. And That's what you need to explain here. What you can try different is you can try a very high, you can charge it to a very high voltage. So then you'd have lots of charges, lots of potential energy to dissipate through the light bulb, and you can imagine the brightness of the bulb would be much bigger. And finally it goes off when there are no charges remaining here. And so write down what components are required to light a bulb, and how does this whole system operates here. Use one or two uh, screenshots. The second one here, it will be a practice for you for next labs, to build your own circuit with light bulb, and you can add resistors, switches, batteries, whatnot. Get your light bulb, a battery, and some wires. Um, you can connect this to your light source. Let me put a switch in here just for fun. Connect that, and okay, so this is a 9-volt battery. I can give any voltage to it, and as soon as I supply, the switch is turned off. Let me turn on the switch, and as soon as I start provide some potential difference. Um, I'm not sure if you have covered the potential. I think you have the current and potential and the voltage and the resistance in your class. So your battery is a source of potential. What it simply does is it provides a required potential difference for the electrons, for the free electrons in the wire to flow. The battery has its own free electrons, and so this 2.2 volts means this is at high potential 2, and that's at 0. So the difference is 2 minus 0, 2 volts. And so the electron sees this potential difference, and the electrons flow through it. Okay, and electrons fall in that potential, and the electrons travel here through the wire, and when they reach inside of the bulb, there is always a high resistance material in it where the electrons lose their kinetic energy to the motion, the energy due to motion of the electron, and that energy is lost here in the form of heat and light. And increasing the voltage means I'm increasing the electron energy, and hence the light bulb grows brighter and brighter. Uh, and Again, this is the electron direction. By now, you may know the difference between the electron direction and the current direction. The conventional current direction is always from positive towards negative. However, the electron direction is always from negative to the positive. Um, no, it's the how we measure current is the rate of change of charge. So it would be more wise to measure, to think, or to write down that the direction of electron is same as the current direction, but it's not. Why? Simply because physicists screwed up. Back then, when it was in the developing stage, everybody thought it was the positive charge that was moving from positive to negative end, and they gave that the direction of the current. But later we know it's the electron that moves around, not the positive charges, and but we stick to the direction, so we still call that the conventional current direction, and hence that's the conventional current. And this might put you in some confusion even later when we do magnetism. You need to understand the direction of electron and direction of current. There's simply opposite. And so what we are trying to explore here is the although this the battery is not, it cannot provide the potential difference forever, so, but for finite amount of time, uh, it it has this constant, it provides constant voltage and constant current, so the battery remains, sorry, the light bulb remains lit up compared to our previous one. The capacitor main difference is we charge it, and once we connect it to the light bulb, see, it has finite amount of charge, and so the light bulb will remain as long as charges are there in the plates, and with large amount of charge, it's brighter and it decays as we go. And here, however, the battery, for finite amount of time, for certain time frame, the voltage and current are constant. It constantly provides that required potential difference and required current for the light to lit. And you just have to write those understandings over here. And so that's that. Again, at the end, research to find a practical application where the energy stored in a capacitor is used. So there are multiple devices. If your keyboard uses the capacitor, and the most practical example would be your um, flash in the camera uses the capacitor. As you can see here in this example, uh, this so this is your built-in capacitor in the camera. When you click your camera, the capacitor draws all the charges from the battery and is stored in the capacitor plates, and as soon as your camera shutter opens, that's when you need the flash. So that timing is set to be exact, and whenever the camera shutter opens, this is your camera flash, your connection switches, and all that stored energy in the capacitor is released at once, and you get the flash from the camera. And there are some more. I would like to do some research and give some examples here, and that should be the end of your capacitor lab.